Hello and welcome everybody. Today in calculus we will be looking at solving for separable variables. So this is a type of differential equation where you can actually solve for the original equation then. So let's go ahead and dive into it. So here are some examples of where you have differential equations where you can solve for it. And this is going to be our first example. So the way we're going to do it is we're going to separate the variables as the name suggests. So that means I want to keep all the y's on one side and all the x on the other side. So here, if it helps, what I'll do is I'm going to go ahead and write the y prime as dy dx first so you can see how that works out. So dy dx minus e to the x is equal to 0. Do you have to do that? The answer is no, but it's just usually nicer so you can see what's happening. So I'm going to go ahead and move the e to the x to the right. So y multiplied by dy over dx is equal to e to the x. Now, in order to get all the x's on the other side, the next thing I'm supposed to do is multiply both sides by dx. So y multiplied by dy is equal to e to the x multiplied by dx. And at this point, because your variables are separated, we can now just strictly integrate both sides to get our answers then. So y squared multiplied by 1/2 is equal to e to the x plus c. Now, your constant plus c, you can either add it to the y side or you can add it to the x side. And since, we're just going to pick one of them, then we'll just go ahead and pick it with the independent variable. The reason why you don't add it to both sides is, well, if you add it to both sides and then you subtract it to the other side, it's still going to be a constant nonetheless. So just pick one side and stick with it. Okay, now what we'll do is we're going to go ahead and solve for what c is by plugging in the initial point that's given over here. So we'll go ahead and plug in 0 for x, and y is equal to -4. So that's what this notation over here is representing. So x is equal to 0, and y is equal to -4. And if we do so, we're going to get -16 times to 1/2, which is equal to 8, is equal to e to the 0, so that's 1 plus c. So that means that c is equal to 7. So nearing the end over here, we now have 1/2 multiplied by y squared is equal to e to the x plus 7. And if we can solve for y, we would like to do so if possible. So I'm going to go ahead and multiply both sides by 2. So 2 times e to the x plus 14. And then finally, we're going to go ahead and take the square root. Now, this is the part where you have to be very careful because technically there is a plus or minus according to what we have right here. And we have 2 times e to the x plus 14. Now, to determine if it's plus or minus, we go back to the initial value that was given. So meaning the point that was given to you. Considering that your y value is -4 in this case, and that means that in this scenario, I have to choose the negative answer because that's the only way to get that. So my final answer is y is equal to the negative of 2 times e to the x plus 14, okay? So when that happens, where you have to take the square root of y or choose between positive and negative, always refer back to the IVP, right, the initial value point, to see if it's a positive or negative value, so that will determine what's going to happen then, okay? Okay, so here's another problem, just kind of like what we just did. What I need to do is solve for this using separation variable. And again, we're going to have an IVP problem, the initial value problem over here, meaning that I gave you the point to solve for c. So first, we'll go ahead and separate the variables then. So dy divided by y minus 1 is equal to 2x plus 1 multiplied by dx. We'll go ahead and integrate both sides. So ln of absolute value of y minus 1 is equal to x squared plus x, and then we say plus c. Once you solve for the antiderivative, it's usually good to solve for what c is equal to and then solve for y just to kind of, keep that, procedure consistent. So we have y is equal to 3 and x is equal to -1. So if we throw all that in, we're going to get ln of 2 is equal to 1 and then -1 plus c. So it looks like c is going to be equal to ln of 2. So go back to the very beginning. So ln of absolute value y minus 1 is equal to x squared plus x and then plus ln of 2. And once again, if you can isolate y, go ahead and do so. But there are times when you cannot, so you have to kind of like assess the situation here. So since I can solve for y, I'm going to go ahead and do that then. We have absolute value of y minus 1 is equal to e to the x squared plus x and then plus ln of 2. Now, optional if you want to change this or not, but I like to in this case. I'm going to say that that's e to the x squared multiplied by e to the x multiplied by e to the ln of 2. And you can see now why I actually simplified it, because this guy right here tells me that this is going to be equal to 2 then. Okay, so once again, looking again as to what we have y minus 1 absolute value is equal to 2 times e to the x squared multiplied by e to the x. Here we have an absolute value, so in order to get rid of it, we put a plus or minus onto the other side. So there's your plus or minus scenario once again. So 1, sorry, not 1, it's going to be plus or minus 2 times e to the x squared times e to the x. And finally move that 1 over, so 1 plus or minus 2 multiplied by e to the x squared times e to the x. To determine if it's a plus or minus, again, we refer back to the initial value problem. So -1 comma 3, and you're wondering to yourself, okay, well, if I plug in the values, right, you should be able to get 3 for the y. Well, the only way I'm seeing you getting a 3 for y is if we choose the plus part in this case, because 1 minus 2 times some positive number is not going to give you something that's bigger. So in conclusion, y is equal to 1 plus 2 times e to the x squared multiplied by e to the x. Okay? All right, so that hopefully wasn't too bad then. Now, this one right here, this is not necessarily a differential equation, but it's kind of like in that form, though. This problem, you're going to need a calculator to solve for, so let's go ahead and look at this together. You have dy dx is equal to x times sine of x. If f of 1 is equal to 3, then f of 2 is equal to the question mark. So the intention of this problem is that, okay, for AB students, you wouldn't be able to solve for it because you don't have integration by parts. For BC students, you do have integration by parts, so you can solve for it. But I need something that satisfies both, A, B, and BC, assuming that it's something that you might not be able to solve for. Because maybe I'll have something like, say, y times sine of x is equal to dy dx instead. So the question is, well, how do you compensate for this without having to use integration by parts then? The best way you can think of it is, okay, well, if you solve for the antiderivative, you're going to have to plug in the initial value point in order to solve for what c is equal to, and then afterward plug in 2. But then another approach of it is you can use FTC2 then. A lot of the times where they give you, like, say, f of 1 is equal to 3, and then they say solve for another value, FTC2 actually works out the best. And here's what I mean. The integral from 1 to 2 of x times the sine of x dx, that means that I'm trying to solve the area under the curve from 1 to 2. And I know to choose from 1 to 2 because, look, over here in the initial value points, they gave you 1 and 2 for x to use. So that's how I know to set up that boundary. Now, if I want to solve for this, what I normally do is I'll solve for the antiderivative, right? So then that means whatever the antiderivative is, we know that that's supposed to be represented as f of x. So that means that this is going to be equal to f of 2 minus f of 1. So that's your FTC number 2 then. So this guy right here, this is where your calculator comes in because you don't want to try to solve for this by hand or use integration by parts. So let's see, we're going to go to the calculator over here, and I did it already on the side. So it's 1.440. So let me go back over here. So let's do the replacement and write 1.440, and that's approximately equal to f of 2, which I'm trying to solve for, minus f of 1, which is equal to 3. So that means that f of 2 is equal to 4.440. And all this without having to actually solve for the antiderivative then. Okay. All right, so now let's look at this last one, which is going to be kind of like a free response type problem where you can kind of figure out what are some of the other things you can do with separation variables. Number 1, or part A, consider the differential equation of the following. Okay, so dy dx is equal to 4 minus y. Let y equal to f of x be the particular solution to this differential equation such that f of 0 is equal to 1. So this is what they call an IVP once again, because it's an initial value that's given to you and it's a problem, IVP. So find the equation of the tangent line to the graph of the solution at f of x at the point 0, 1. Use the line to approximate 1.5. So they don't want us to solve for the original equation just yet, but they want us to solve for the tangent line first. Well, the tangent line, if you recall, you need to know what the slope is, and also you need to know what the point is. So the slope, that is going to be equal to dy dx, because that's what the derivative represents. And I want to solve for the slope at the coordinate that they give you. So that is going to be 0, 1. So you take that point and plug it into your differential equation then. So 4 minus 1 is equal to 3, and that's going to be your slope. The point that you have, right, the coordinate of where you're trying to find a tangent is supposed to be at 0, 1. So that means my equation of the tangent line is going to be equal to y minus 1 is equal to 3 multiplied by x minus 0. And once you get that equation of tangent line, then they want you to use it to approximate f of 1.5, because if you remember, the tangent line and the slope are almost identical to each other for small values of x, or for local values of x. So here we're going to go ahead and plug in x is equal to 1.5. So y is going to be equal to approximately 3 times 1.5 and then plus 1, and that would give you 5.5. So what I did right there, what I solved for, is supposed to be kind of like an estimation of what's the next point that's going to be on the curve. And if you think about it, this is really just Euler's method with one step, because they told us to do it one time. Now, if you're doing Euler's method for 2 steps, they'll say approximate what is f of 2 using, like, say, delta x is equal to 0.5, or some sort of thing that indicates that you have to do it 2 times then. Okay, so that's the first part. Pretty straightforward, hopefully. Part B, now I want to find out what is the limit as x approaches towards 0 of the following. So this one's a little bit trickier. Limit as x approaches towards 0 of f of x divided by 6x. Now, usually for a limit problem, we say go ahead and plug it in just to see what happens. If you do so, you're going to get f of 0 divided by 0 right there. And f of 0, according to the IVP, is supposed to be equal to 1 in this case, right? So let me just check. Yes, it's equal to 1. So I'm going to put 1 over 0 in this scenario over here. And when you get 1 over 0, then that means that this is going to be does not exist. Now, you technically can write infinity or either one of those. I think it will be acceptable. But in this case, I'll just go ahead and write it does not exist, just to make it, just so that I don't lose any points in this case. Okay. Now, it's a little bit different if you get 0 over 0, because if that happens, then that means you're going to have to use L'Hopital's rule. So that is where you're going to have to plug in afterwards to do the indeterminate form. So hopefully you don't have to do that in this case. Okay, finally, part C, find a particular solution to that differential equation. So that's basically all the stuff that we've been doing so far. So dy dx is equal to 4 minus y with the IVP of f of 0 is equal to 1. So I'm going to go ahead and isolate from both sides. So dy over 4 minus y is equal to dx. Integrate both sides. So ln of absolute value of 4 minus y with a negative in the front because of the chain rule working backwards is equal to x and then plus c. Once we get to the antiderivative, we're going to go ahead and plug in the initial point to see what we get then. So negative ln of 4 minus 1, so that's absolute value of 3, is equal to c, because it's 0 plus c in this case. So that means that c is equal to negative ln of 3. We could get rid of the absolute value because it's an absolute value of a positive number. So if we can solve for y, we're going to go ahead and do so then. So in here, we're going to have negative ln absolute value of 4 minus y is equal to x, and then we have minus ln of 3. I think what we'll do is we'll get rid of the negative first. So ln of 4 minus y is equal to ln of 3 minus x, just to flip the other side. Get rid of the ln, so 4 minus y is equal to e to the ln of 3 minus 3, which you can then write as e to the ln of 3, and then we have divided by e to the x. So let's see, I'm kind of losing space, so I'm just going to continue over here. So 4 minus y is equal to ln of 3, oh sorry, e to the ln of 3, that's really just 3 then. And then divide by e to the x, as I said. Absolute value is still there, so I can't quite get rid of it yet, so we still have that there. So next we'll apply the absolute value. So 4 minus y is equal to plus or minus 3 divided by e to the x. And then finally we have 4, and then we can put this onto the left-hand side. So that we'll say plus or minus, or technically minus plus, but it's still the same thing. 3 divided by e to the x is equal to y. Okay? Take a look at your IVP over here. Since you have y is equal to 1 when x is equal to 0, then that means it's most likely I'm going to choose the negative answer because it's 4 minus 3 is equal to 1. So my final answer is 4 minus 3 divided by e to the x is equal to y then. Okay. All right, well, there you go. Thank you so much for watching, and I will see you guys next time. Have a good one. Bye-bye.